This time around, our mood has changed to revision. So we are picking, as part of our ensuring that you're prepared for the upcoming exam, we're picking up some past papers and going through them. So our first stopover is Thermodynamics. This paper was written in August 2024. So we'll go through this one by one from question 1 up to question 8. So without wasting your time, let's straight away sample what question 1 said. And I have to say that during our revision, you realize that we took our time when we were discussing topic by topic to go deep into the various items, discussing the principles. So when we come to the revision, some of the items we'll be talking about will be referring to what we learned and making sure that we go straight to the working without spending too much time on discussing principles from scratch. So let's pick up question 1. So question number 1 was talking about definitions. Explain the following terms. Boundary. So in thermodynamics, a boundary is supposed to be that surface separating the system from the surroundings. An open system is supposed to be a system that is free to move. In that way, we are saying that it exchanges matter between the surroundings. At the same time, not only matter, but also energy with the surroundings. A closed system doesn't do that. The system or the working substance remains within the fixed boundaries, within the boundaries, without crossing or causing any movements. Adiabatic system, we're talking about a system where the heat transfer is 0. There's no heat transfer there. So here's our question. The pressure reading given below are obtained from different points in various thermodynamics. These systems express each pressure reading in kilopascals, assuming the local barometer gives a reading of 760 millimeters of mercury. So what this means is that where we are going to be given gauge pressure, we'll refer back to this, because barometric pressure, or we call it atmospheric pressure, and that is our first stopover. We'll try to calculate that one. So the questions are, let's calculate 8 centimeters of mercury. The second one is 30 centimeters of mercury vacuum, followed by 1.35 meters of water, 4.2 bar. So in our data provided, we are saying our first stopover is this atmospheric pressure. The atmospheric pressure that we've been given is equivalent to 760 millimeters of mercury. So we convert this to pressure. It becomes, if you divide this by 1,000, you get 0.76 meters. Multiply it by the specific weight of mercury, which is 133,416. Specific weight of mercury, you can even say 13,600. 13,600 multiplied by 9.81. Then it gives you the value we have. Or you can use the specific gravity of mercury, which is 13.6, multiplied by 9810. The value is still the same. So with this product, we get our actual barometric pressure, atmospheric pressure, as 101,396.16. With that sorted out, let's get to work. Part 1 is saying 80 centimeters of mercury. So just go to the height of mercury, we convert it to meters. Centimeters mean that you divide that number by 100, so you get 0.8. So referring to the formula for pressure, which is P is equal to specific weight by height. That's what we're going to be referring to. Then also, we're dealing with mercury. So this is the value coming from that expression where we're saying density of mercury times acceleration due to gravity. So we get 133,416 newtons per square meter, 133,416 pascals. From this formula, we substitute. Our specific weight is 133,416 multiplied by the height, which is 0.8. Our answer, 106,732.8 pascals. Let's repeat the same now. Also, that's 106.733 kilopascals. The question was saying that all the answers should be expressed in that unit. "30 centimeters of mercury vacuum." When we say vacuum, we're talking about negative pressure, which has an effect of suction as compared to what positive pressure does, the opposite of what positive pressure does. So 30 centimeters, meaning we're talking about like negative 30. So this 30 divided by 100, you get 0.3 meters. Again, we're dealing with mercury, so it's 133,416. And when you go to the same formula, P is omega H, we do the substitution. In place of omega, we put the specific weight of mercury. Then we multiply by the height, which is 0.3. So from that product, we get our answer, which is 40,024.8 newtons per square meter. But the rule we're given is that all of them should be expressed in kilopascals, meaning that the answer we found, we divide by 1,000. So we get 40.025 kilopascals. Negative because this is vacuum. Next, we have 1.35 meters of water. 1.35, that is the height. It's already in the SI unit we want. Water, the specific weight is 9810. It's standard. So we substitute. In place of omega, we put 9,810 multiplied by the height, which is 1.35. Now, the secret is that what we were told is that this is gauge. This is gauge pressure. What it is that when you're given gauge pressure, here we're looking for absolute values. So it means we're going to invite the atmospheric pressure. So 9810 times this, we get our gauge pressure as 13,243.5. Now, having done that, you can now get the absolute pressure, where you're going to say the gauge pressure plus the absolute pressure gives us, plus the atmospheric pressure. Okay, this is gauge pressure plus the atmospheric pressure. That is how we convert now to absolute pressure. So from there, you get 13,243.5. The answer we got plus the atmospheric pressure that we calculated right from the beginning, where we said it is 760 millimeters of mercury. So 101,396.16. That is our answer, 114,639.66 pascals. Again, all of them should be expressed in kilopascals. So again, we divide by 1,000. So our answer is 114.693 kilopascals. Always important to make sure that you check the unit that has been given, the unit that has been specified for you to use. Because if you end here, your answer is incomplete. The other condition was that all these answers must be expressed in kilopascals. (4.2 bar). Here, basically, we're just converting. 1 bar represents 100,000 pascals, or 10 power 5. So we say 4.2 times that same number. Now we get 420,000. And after that, we convert it to kilopascals. Just divide it by 1,000. Our answer is 420 kilopascals. Let's get to the second question. Definitions again. Define the following terms. First, there's potential energy. Potential energy, we say that energy possessed by substance due to its height above the data. Internal energy, the state of a function that defines the energy of a substance in the absence of effects due to capillarity, or the energy inside or possessed inside your working substance. Then the next question is asking us to distinguish or differentiate between non-flow and the flow process in thermodynamics. So in a non-flow process, we are saying in this process, a fluid, the working substance is confined to the boundaries of the system. But in a flow process, this is where we have an exchange of the matter and energy within the boundaries. So energy and matter freely moves across the boundaries because that is a flow process. So that is the difference between the two. The question here is saying, when a simple experiment was conducted on an engine, it was observed that self-ignition would occur in the engine using a certain brand of petrol if the temperature due to compression reached 350 degrees Celsius. Determine the final pressure in each case and the highest ratio of compression that can be used to avoid pre-ignition if the law of compression is given by PV power 1.3 is equal to constant. So we're calculating two things. Number one is the final pressure, which we can copy to. The second thing we're looking for is the volume ratio, the ratio between V1 and V2. So given those two conditions, the first one, we're using PV power 1.3 is equal to constant, or PV power 1.4 equals constant. Now, what do we have? We have been given the conditions that the temperature, the inlet temperature is 27 degrees Celsius, inlet pressure 1 bar. But this is an assumption that has been provided also in addition to what is already there. Now let's see, bring together the information. Temperature 1, which is 27, we add to 73 so we can convert it to Kelvin. So it becomes 300 Kelvin. Temperature 2 is 350. Add to 73, you have 623 Kelvin. So pressure 1 is 100 kilopascals. So it's 100,000 pascals. Let's start with the first one. Assuming that we're dealing with this law, which is P V raised to power 1.3 is equal to constant. The other way of writing this one is where we say P1, V1 power 1.3 is equal to P2 V2, that's V2 power 1.3. This is the same as what we have on top, and you can write it in that format or any other. Now, considering that this is an adiabatic process, while the volumes behave like this, the pressures relate in this manner where we say P1 T1, P1 over P2 is equal to T1 over T2 raised to power gamma over gamma minus 1. So what do we want? We want pressure 2. So just do the substitution. Pressure 1 was given as 100,000. Pressure 2, we don't know. Temperature 1 is 300. Temperature 1 is 300 Kelvin. Temperature 2 is 623. Raised to power, that adiabatic index is 1.3. Divide by 1.3 minus 1. So 100,000 over P2 is equal to 300 over 623. When you subtract these two, you end up with 0.3. On top, there's still that 1.3. So our answer for the final pressure is 2,372,000, then 772.49 pascals. The question was requesting for two things. Apart from the pressure, we also need the volume ratio. Volume ratio. Volume ratio is simply the ratio between the volumes under this law. So that is where we will now get back to this relationship. P1 V1 power gamma is equal to P2 V2 power gamma. So if you now make V1 over V2 as the subject of the formula, on the other side you have P2 over P1 raised to power 1 over gamma. Now, with this, we can just do the substitution because this is what we're looking for. Pressure 2 is the one we just from finding 2,372,772.49. Pressure 1 is 100,000 raised to power 1 over 1.3. So when you enter whatever is in the brackets here, you end up with 23.772 there, raised to power 1 over 1.3. And once you compute our V1 over V2, the volume ratio comes out as 11.426. When we're using this 1.3 as our adiabatic index. Let's repeat the process. What if we now have PV per 1.4 equals constant? Here, we start again with the pressure. P1 V over P2 is equal to T1 over T2 raised to power gamma over gamma minus 1. And we do the substitution. Our P1 is 100,000. Our P2 is just P2. Then T1 is 300. T2 is 623 raised to power 1.4 divided by 1.4 minus 1. Okay? Then we proceed. From there, we are saying 1.4 minus 1 is giving us the 0.4. And then the number, the final answer comes out as 1,290,576.556 pascals. But we are not done. What about the volume ratio? The same thing. For the volume ratio, we're saying P1 V1 is equal to P2 V2 You make V1 over V2 the subject, then you have P2 over P1 raised to power 1 over gamma. So V1 over V2 is equal to, in place of P2, we have this, which you already found, 2373. Oh, in fact, sorry, this one is supposed to use this number 12905. This is the one we're supposed to put there. I think this one I'll edit. That's the number you put there and you substitute. So this number will also change. Then finally, you get your answer there. So here, I'll just edit here. The number we should have there is the same one we got here, which is 1,290,576.556. Okay, so basically that is a repeat of the other question, but we're using 1.4 and the other one we used 1.3. Third question. As usual, explanations start first. Isobaric process, we're saying this is a process carried out at a constant pressure. Isochoric, carried out on a gas at a constant volume. Isothermal, you keep the temperature constant throughout the process. And here is our part B. So here we're told mass of 2 kg experiences 3 process like that. Calculate the network done during the 3-process cycle. 1 to 3 is isothermal. So provided pressure 1, we don't know. Pressure 2 is the same as pressure 3. It's 100 kilopascals. This is the one we can see here. Volume 1 is the same as volume 2. It's 2. Volume 3 is 10. Now let's start with considering 1 to 2. Isothermal process. In fact, it's not even 1 to 2. The isothermal is actually 1 to 3, according to the diagram. So we have P1 V1 is equal to P3 V3. P1 V1 equals P3 V3. And we have, therefore, from there, we make P1 the subject. We have P3 V3 over V1. And we get our P1 where we are saying, because this is an isothermal process, pressure 3 is 100, volume 3 is 10 over 2. Well, this is now for volume 1, which is equal to volume 2. So with this, we get our P1 as 500 kilopascals. Let's go to the net work done. The net work done is going to be the difference between the work done during the isothermal process and the work done during the isobaric process. We subtract what is the isothermal process work done minus the isobaric process work done. So isothermal, which is 1 to 3, minus isobaric, which is from 2 to 3. So in this case, we say P3 V3 ln V3 over V1 minus P, then the difference in volumes. And this is a constant pressure. So it's saying 2 and 3 are the same. So this P is supposed to be P2 or P3, same thing. Now, here we have our values. First, we have work, a P3 is 100 multiplied by volume 3, which is 10. Ln V3 is 10, then V1 is 2, minus. Then there we include the same pressure, which is pressure 3, the constant one. And we get 10 minus 10 is for V3 minus V2, which is 5. So we have 1005 minus the 500. And our work done comes out as 1,109.438 kilojoules. Question 4. Definitions for mixed phase, saturated phase, superheated vapor, and supercooled vapor. A mixed phase, we're saying that this is where two or more phases are existing, they are coexisting, and they're still in equilibrium. So hence, we simply consider it to be mixed. Saturated, excuse me. So here you have a substance existing in either gas or vapor phase in equilibrium at a particular temperature and pressure. Then we say here we have reached saturation phase. Superheated vapor, here is a case where above that saturation temperature, where the vapor you can almost consider to be boiling, you add, heat it above that, then it becomes superheated pressure. Of course, during that time, you will not have any liquid present. Supercooled, this is interesting because what you see here is you cool a liquid below its freezing point, but that liquid doesn't freeze. So we can say this is supercooled, very dangerous liquid. So here's our question, says a mass of fluid, pressure 3 bar with specific volume 0.18 cubic meters per kg. Then we're told the fluid is contained in a cylinder behind the piston and allowed to expand reversibly to a pressure of 0.6 bar according to the law PV power 2 equals C, where C is constant. Calculate work done by the fluid on the piston. As usual, let's start with the data. Pressure number 1 is 3 bar. So we convert it to Pascal. So it becomes 3 times 10 power 5. So it's 300,000 pascals. Specific volume is 0.8 cubic meters per kg. But we have to interpret this. It's saying cubic meters per how much? Per 1 kg. Meaning that from here, I already have V1. First of all, I have mass 1 kg. And I also have V1 as 0.18 cubic meters. Pressure 2 is 0.6 bar, meaning 0.6 times 10 power 5. So when you do that, you get 60,000. PV squared is equal to C. That's the law we are using, meaning that P1 V1 squared is equal to P2 V2 squared. This is the formula we've been told to use, this one. With this in mind, let's calculate the work done. Calculating the work done is simply with that kind of an expression. First of all, we're missing V2. If you make V2 the subject, you say V2 is equal to square root of P1 V1 squared over P2. And of course, you can substitute. Our P1 is 300,000 multiplied by V1, which is 0.18 squared over P2, which is 60,000. So from there, you get V2 as 0.162 square root, and our answer is 0.4025 cubic meters. Now we are ready. Work done is P1 V1 minus P2 V2 divided by gamma minus 1 for an adiabatic process. And then you can now just substitute P1. In fact, this is more of a polytropic process. So our P1 is basically 300,000 times volume 1 is 0.18 minus pressure 2 was 60,000 times volume 2 was 0.42025. Below there, our gamma is 2 minus 1. And that's what we have now. After multiplication, we end up with 54,000 minus 24,150. So then our work done is 29,850 joules per 1 kg. Question number 5. This question, we've been given the volume, the capacity. Vessel having a capacity of 0.05 cubic meters contains water saturated at a temperature of that. Water and saturated steam. So then we need to find, together, we thought that the liquid, which is the water, is having a mass of 10 kg. So we need to determine the pressure, the mass of the mixture, the specific volume, the specific enthalpy, the specific entropy, the specific internal energy. Now, if you go back to you check the values for that temperature, which have already been provided. Saturation pressure is 36.5. The VF, specific volume for the fluid, is 0.001239. Volume of the gas is 0.05. HF is 1061.4 and HG 1740.2. SF, which is entropy, is 2.7474. And also, we have SFG, which is 3.3585 Kelvin. These numbers are part of the data, already picked from the tables, so you don't need to worry about the tables. Now, with this information, let's now get to work. The data, we told the total volume of the mixture is 0.05, and the mass for the gas is actually 10 kg. Then we proceed. We also have, you need to find the pressure of the mixture. When we talk about the pressure of the mixture, we don't even need to stress. Look at the information provided. We were given the saturation pressure. That is actually our pressure, 36.5. Hence, 36.5 by 10 power 5 pascals, because this was in bar. Mass of the mixture. For the mass, we go to total volume first of all. The volume we've been given is 0.05. Now, one thing you realize is that this volume, which is 0.05, when you multiply the mass by the specific volume, you're going to get the mass of this first part. The mass of, the volume of the liquid, because the mass will cancel out. This one also for G, which is for the gas, for the vapor. Mass of the gas times the specific volume of the same gas, the mass will cancel out, you end up with specific volume of the gas. When you add them, they'll give you that total that you're looking at. Because here you're multiplying by the mass present, And true to that, this is our total. The mass of the gas, of the liquid present is 10 kg. Specific volume of this same liquid is 0.001239 multiplied by, or rather plus, mass of the gas we don't know, times this specific volume of the fluid, of the gas, which was given as 0.0546. Our target is this for now. So making mass of the gas the subject, you end up with the 0.6888 kg. Just like the other one, this is also in kilograms. Then we continue. Now that we have the mass of this vapor, the mass of this gas, we can add them. Mass of the gas plus the mass of the liquid or the fluid. So 0.688 plus 10. Our total is 10.6888. Specific volume. First, we cannot talk about this one before knowing this dryness fraction. The dryness fraction tells us how dry your vapor is. If it's completely dry, then the dryness fraction is 1. So in this case, we're going to say the dryness fraction is that mass of the gas divided by the total mass. The mass of the vapor divided by the total mass. So we have the mass of the vapor is 0.6888 divided by the total mass, which is 10.6888. And what do we get? We end up with the dryness fraction of 0.06444. With that, we can now proceed with finding the specific volume. So the specific volume is VF plus X VFG, which is like the difference between VG minus VF. Here I'm saying V, but in actual sense, this is letter nu. Greek letter nu is slightly different from the V. But for the sake of simplifying, let's keep calling it that. So in the VF, we have 0.001239 plus the dryness fraction is this number we have here, 0.06444. Then open the brackets. VG is 0.0546 minus VF was 0.001239. Now, with all that, our specific volume becomes 0.004677 cubic meters per kg. So what I was saying is this. This part, you can also write it in this way, where you say specific volume of the fluid plus X multiplied by the specific volume of the combined fluid as well as the gas. So this VFG or nu FG is the one that gives us, it's the same as this, the difference between the specific volume of the gas and the specific volume of the fluid. Let's go to specific enthalpy. We'll write the same thing. First, let's calculate this one separately. If we want, we can even plant it like that, but for a change, I decided to do it that way. So HF minus HE gives me 1740 for HG minus the number we're given for this is 1061.4. So our answer is 678.8. 678.8. And then with that, we can now go to our full expression, where we're saying the total specific enthalpy is HF plus X HFG. HF is 1061.4 plus X is 0.06444 times the HFG is 678.8. So this is 1,105,142. This is our answer for specific enthalpy. Excuse. Entropy, the same thing. S equals SF plus XSFG. So you have S is equal to, our SF is 2.7474 plus X is 0.06444 times 3.3585. Then our S is 2.964. Internal energy, specific internal energy. Now, one thing you notice about the question is that the values for internal energy, these were not provided. Meaning that basically there was a problem with the question. So for me to proceed with this, because we're revising, I had to go in the table and pick those values before proceeding. So then we substitute our UF is 1083.2. Remember, what we've written here is the same as UFG, but I'm just planting it directly. We can either write it in this format or where you put FG there. X is 0.06444. Then UG is 2573.2 minus UF, which is 1082.3. So with that, you get your specific internal energy as 1,178.374 kilojoules per kg. Let's go to question 6. Here, talking about some definitions. A fuel, just a substance that is able to react with oxygen and produce a lot of heat. A reactant. So here, that is one that is supposed to undergo some chemical transformation and thereby produce one or more products at the end. Combustion, a process where the fuel reacts with oxygen and producing a lot of heat energy, that is burning or combustion. A weak mixture is a mixture where the appropriate air-fuel mixture, you end up with more air compared to the fuel. If you do the opposite, then it becomes a rich mixture. If you have more fuel compared to the air, the actual values expected, if you end up adding more, then you end up with a rich mixture. So that's that one. And each of them, of course, what I keep saying is in our technology, they have implications on the performance of an engine and how it will behave. If it's rich or weak, you have different reactions or different behaviors from the engine. And also the environment, especially if you're dealing with diesel. Now here we are. B, the percentage composition of a sample of liquid fuel by weight is 84.8% carbon and 15.2% hydrogen. Calculate or determine weight of air needed for burning 1 kg of this fuel and volumetric composition of the products of combustion if 15% excess air is supplied. Let's pick up information provided. 100% is 100 over 100. So how are we sharing? When we say 100 over 100, 100 divided by 100. So if you cancel this, it means I'm dealing with 1 kg. The same one mentioned there in part 1. So I'm dealing with 1 kg of the fuel. Now, how have we shared this 1 kg? First of all, 84.8% is for, which one is this? Carbon. So meaning I'll say 84.8 divided by 100. What I get is now a fraction of that 1 kg. So I have 0.848 kg. I do the same for hydrogen, which is 15.2%. So 15.2 divided by 100, I have 0.152 kg. If I add this number and this number, what I should end up with is 1 kg, because basically I'm just splitting up the 1 kg. So going back to our analysis of the oxygen needed, because that's where I'm going to start from, I'll have carbon. If you remember the complete combustion of carbon, where you say 1 kg, in fact, it's C plus O2, and it gives us CO2 as the products of that combustion process. So we're talking about the complete combustion of carbon to carbon dioxide. For you to burn 1 kg of carbon, you need 2.667 kg of oxygen. And in the end, you end up with 3.667 kg of carbon dioxide. So this comes from there where we plant those numbers for carbon. We know it's 12 for oxygen. In 16 times 2, we get a 32. Then we add the total. Then the products there end up being 3.667 kg. So that is where this number is coming from. It's from the chemical equation balanced out nicely, and then you transpose the equation to expose 1 kg to make sure you remain with 1 kg of the fuel element. Do the same for hydrogen. For hydrogen, when you say H2 plus O2, in fact, when you balance that equation, you have something like this. It's 2H2 plus O2 is equal to, what do we get? We get that water vapor. Basically, we're simply calling it as water because in the chemical equation, that's what we can see. So this equation is balanced. When you balance it out, now try to put the mass numbers. You have here, there's 4 kg, there's 32, there, another number. So you end up with 8 kg of oxygen for 1 kg of hydrogen to be burnt, producing 9 kg of water vapor. When we come to the products of combustion, we'll come back to the 9 kg. For now, because we're calculating the oxygen, we use the 8 kg for oxygen. So since we're having we're having a different mass, it's not 1 kg. So we multiply that by the 8. 0.152 times 8, we have that 1.216. Next, let's add these two. So you have 2.261616. Don't worry about my length and decimal there, but to be trimmed as we go. Then you add with this other one here. What you get for oxygen now is 3.477616. This is our total mass of oxygen. This is our total mass of oxygen. So having known the total mass of oxygen, now you are ready to find the total mass of air required. So we say that total mass of oxygen divided by 0.23 give us the mass of air required. We know that by mass, the composition of oxygen in the air is 23%. So therefore, that's how come we're having this 23. By volume is 21%. For now, we're dealing with the 0.23 because we are what we've been given are the masses, and we're dealing with the mass according to the question. So the answer we got was 3.477616 divided by 0.23, and our answer is 15.12 kg. What are we saying? You need 15.12 kg of air in order to burn 1 kg of this type of fuel we've been given. So that is our answer. Don't worry about the use of the word weight. It's a jargon for this topic. We're saying the weight of air required, but yet the numbers given are in those masses. So it's 15.12 kg of the air, and we leave it there. Let's go to analyzing the products of combustion by volume. So before we can get there, let's analyze them by mass. Now, first, water vapor, which is H2O, we said the complete combustion of hydrogen to water vapor produces 9 kg of water vapor. So that 9 kg of water vapor, in this case, we're not burning 1 kg of that, no. It's 15.2%. So 15.2 over 100 is what we had. So when we multiply 15.2 over 100, which is like 0.152 times this product, we get this as the actual end result. Can we repeat the process also for carbon dioxide? In the case of carbon dioxide, we said the complete combustion of carbon to carbon dioxide, the products are 3.667 kg of carbon dioxide. Now we were told that this carbon dioxide was 84.8% present. So 84.8 present. The carbon, the element carbon, it relates to what will come out. So with that in mind, we have 84.8 divided by 100, giving us 3.109616. Then we proceed. What about nitrogen? Nitrogen is a very stubborn element when you're dealing with combustion because it goes in and comes out the way it was, untempered. But unfortunately for this one, we're told there was excess air that was added. 15% excess air was added. So meaning, in addition to 77% of what you've been provided, we also add 15% of it. So the quickest way to do it is to just say 100 plus 15, which is like saying 115 over 100. We multiply by that, it will give us, it will compute everything added also to, add also the excess air. Meaning you find you are adding 1.15 multiplied by 0.77 multiplied by the air that we calculated here, which was 15.12. And your result is this. The combustion is complete, meaning that we're supposed to end up with 0 kg of oxygen. But unfortunately, this combustion process, we were given the excess air, 15% excess air. So meaning, from that 15%, we'll go back to the oxygen that we calculated. We calculated that the oxygen needed is 3.477616. So what is 15% of that? Just like here, we're also including the 15% added to what is already there. But this time around, this one basically was supposed to be zeroed because it's consumed, but it's the excess air where this one is leaving. So 15% of the oxygen present, 15% of this oxygen we calculated, and the oxygen that we calculated was 3.477616. The answer is here, 0.5216424. And that is in kilograms. Then let's now go to the composition. We add them now, all of them, because we want the total. Now here what I emphasize is that if you want, you can do this. You can also plant it in the table, but deliberately, I wanted it to be here so that I can explain thoroughly where we're coming from. The total mass is, we are going to add this plus that, plus that, plus that. Then we will find out the percentages that are being represented by each of them, because this time around we're dealing with the products of combustion. So I add water vapor, the mass 1.368. I'm adding carbon dioxide 3.109616. I'm adding nitrogen, which is also, of course, taking care of the excess air provided, so 13.8876. Then I'm also adding the nitrogen the oxygen that has survived, which was hidden in the excess air, 15% of that, so 0.52164424. So the total I get from this computation is 18.388018. Please don't worry about this. You can end your number here and avoid making it look lengthy and also making your work look longer. Otherwise, if you're comfortable, there's no harm. So here, 18.388, this is the total mass of the products of combustion. Now let's express each of these as a percentage of the total mass of the products. So we'll start with water vapor. So we'll take this, divide by the total, times 100. Carbon dioxide, we'll take the answer we have here, which is 3.109616, divide by the 18, also multiply by the 100. We do the same for this. We do the same also for oxygen. Starting with water vapor, like I said, 1.368 divided by 18.388 times 100. I get my percentage and I'm safe now, I'm home. The next thing, I repeat the process for carbon dioxide. The products for carbon dioxide, the mass was 3.109616. I divide by the total, which is 18.388, times 100. The answer I get is 16.91. Let me repeat. Nitrogen, the answer we got was 13.38876. So I divide by 18.388. You will notice that nitrogen ends up with a bigger composition, 72.81. I repeat, for oxygen, what we had was 0.52164424. So I divide by 18.388 times 100. My answer is 2.84%. Now, when you add these answers we have here, add 7.44, 16.91, 72.81, and 2.84, you should get back your 100. You should have 100%, because these products of combustion, the total is supposed to be a full package, which is 100%, and this is how they've been shared. Now, going further, let me introduce our table. In this table, what I've just calculated, I could have included another column there to do that, but I thought that was going to be to just like crowd our work. So the water vapor, the answer we got was 7.44%. 7.44%. So what I'm going to have is percentage by mass divided by the relative molecular mass. What do we mean by this RMM? We pick the element like water. The composition of this water is 2 atoms of hydrogen and 1 atom of oxygen. The mass number for a hydrogen atom is 1. So 1 times 2 gives me a 2. The mass number for oxygen is 16. So if I add the 2 plus that 16 from this, that is where this is coming from. So I pick the percentage, which is 7.44, divide by the 18. Then I get this number here. Next, I do the same for carbon dioxide. I know that carbon, it is in 12. plus I'm actually having 2 atoms of oxygen. So I'm saying 2 times 16. You can see that 2 times 16 gives me 32. So if I add 32 to 12, I should be able to get 44. So I get the percentage, this number I have here, put it on top, divide by the relative molecular mass there, which is 44. The next thing is for nitrogen. Nitrogen, the mass number is 14. And we only have 2 atoms of nitrogen. So 14 times 2 gives me the 28. So 72.81 divided by the 28. This is just this number here I have. So I have 2.6. Then I also have oxygen. Oxygen is 16. So if it says 16 times 2, I have 32. So I bring that 2.84, put it on top, divided by 32, and I have 0.08875. Now, with these answers I have here, I can add them. This, plus this, plus this, plus that. We've already used the relative molecular mass relating now to the volume, meaning this total I have, I can now start expressing this as a percentage in volume. Meaning this answer I have, divide by the total, will give me the percentage of water or water vapor that I have in the products of combustion. So I have 0.43 or 413 divided by 3.48605 times 100. Can you see my answer? 11.85%. Let me repeat this one. With carbon dioxide. With carbon dioxide, I have 0.3843. Divide by the total, which is 3.48605, times 100. What I get is 11.02%. All the answers we're getting here in percentage. So that is in percent. Let me go to our stubborn nitrogen. Nitrogen, I got 2.6. So 2.6 divided by the total that I have here. 2.6 divided by 3.48605 times 100. I have 74.58. Finally, there is oxygen, 0.08875. I divide by this total. So 0.08875 divided by 3.48605 times 100. My answer is 2.55%. Now, when you leave this table like that, practically you found your answer. But for the sake of being explicit, making sure that you interpret what you got in the table, what you are telling us is that by volume, the water vapor is 11.85%, the carbon dioxide is 11.02%, the nitrogen is 74.58%, the oxygen is 2.55%. On condition that in this combustion process, we are given excess 15% of air. Excess air of 15% was added, and this is the result. So this is the composition of the products of combustion by volume. This is what we have. 11.85% water, 11.02% carbon dioxide, 74.5% nitrogen, and 2.55% oxygen. These are our products of the combustion process, and we are good to go. Speak up, question 7. Definitions as usual. We have an ideal cycle. So when we're dealing with an ideal thermodynamic cycle, We're dealing with a thermocycle that serves as a benchmark or as a reference for evaluating efficiency in the real world, because in reality, those efficiencies are normally lower due to other realities we face. Then the actual cycle, this is the one that you obtain in the real world. It's away from that ideal cycle, so you find that there are losses and there's things that cannot be reversed. A standard efficiency. So this one talks about a measure of the efficiency of an internal combustion engine. Or of course, we're talking about a thermal cycle, assuming that the working fluid is air. And let's ignore the effects that will come from the chemistry of the combustion process and name it, because that may also bring in other drama. Relative efficiency. Here, we're talking about comparing the actual efficiency that you get to the ideal efficiency. So actual efficiency divided by ideal efficiency, that gives you the relative efficiency. Here's our question. A mass of air weighing 0.5 kg executes a Carnot power cycle having a thermal efficiency of 50%. The heat transferred to the air during the isothermal expansion is 40 kilojoules. At the beginning of the isothermal expansion, the pressure is 7 bar, the volume is 0.12 cubic meters. Specific heat at constant volume, which is CV, is 0.712. Specific heat capacity at constant pressure, CP, is 1.002008 kilojoules per kg Kelvin. Let's go to the data. So what we're being required to find, we need the maximum and minimum temperatures for the cycle. And it has to be in Kelvin. Second one, the volume at the end of the thermal expansion in cubic meters. Heat transfer for each of the 4 processes in kilojoules. That's the third one. Let's go to the data. The mass, 0.5 kg. Thermal efficiency, 50%. Heat energy during the isothermal expansion is 40 kilojoules. Pressure 1, 7 bar. This is the beginning of the isothermal expansion is 0.1 in a Carnot cycle, in a standard Carnot cycle. So volume 1 also has been given, it's 0.12 cubic meters. CV is 0.712, CP 1.008. Let's talk about the maximum and minimum temperatures for this. A Carnot cycle is a cycle that gives you the maximum efficiency you can get for any 2 temperature ranges, maybe 10 degrees, 100 degrees. You try to calculate. The efficiency you get between those 2 cannot be exceeded in the real world, because that gives you the maximum efficiency for our cycles. Now, first things first, let's find the characteristic gas constant, which is R. I must mention here that this is for R. R is equal to CP minus CV. In case you're looking for gamma, gamma adiabatic index is CP over CV. That's how they relate. And depending on which one has been provided, which one you're looking for, these 2 expressions become handy. Sometimes you can even mix them up or make one of them the subject. So in this case, we're looking for R. CP and CV have already been provided. CP is 1.008 minus the CV is 0.721. Then when you subtract those, your answer is 0.287 kilojoules per kg Kelvin. We don't want this kilo in our working. We want it to be converted to joules per kg Kelvin so that we move smoothly. So that's why we end up multiplying by 1000. When you multiply by 1,000, you have 287 joules per kg Kelvin. So that is our R, the characteristic gas constant. We will need it as we go. And I'm emphasizing that the formula we're using is this. The other special formula we have which relates these constants is this one. Adiabatic index is equal to Cp over Cv. And then the rest can fall into place depending on what parameters are available. Point 1, we can apply the isothermal process PV equals mRT. And since we're dealing with the constant temperature process, so T1. So P1 V1 is equal to mR T1. Our P1 is 7 bar. So 7 times 10 power 5. V1 is 0.12 is equal to, our mass is 0.5 multiplied by R, which is 287, multiplied by T1. In this case, our T1, we are yet to find it. So making T1 the subject, you end up with 585.366. Thermal efficiency is 1 minus T3 over T1, where T3 is the lower temperature, T1 is the higher temperature. So when you substitute, our thermal efficiency is 0.5. In the brackets, I have 1 minus the T3 we don't know, divided by 583.366. With that, we get our T3 as 290.68. Always pay attention to the units that have been specified. In this case, the question was saying, express these temperatures we are getting in Kelvin. So here we are leaving it in Kelvin. If it had said we convert to Celsius, we're going to subtract the 273 and convert backwards. Even here, the same thing. But as it is, we leave the answer like that. So this is 585.366. The other one is 290.68. The volume at the end of the isothermal expansion. So with this one, we go back to the formula for the heat added. We were told that during the isothermal expansion, the heat that was generated is actually 40 kilojoules. So we use this formula and make use of the 40 kilojoules to reveal that volume. So when I come here, in place of heat, we're putting 40,000. The mass is 0.5. R, 287. Then T, 585.366. Ln V2 over V1. Then here, of course, when you multiply everything, you end up with 84,000.021. Here we still have the 40,000 representing the heat energy. Then ln V2 over V1 is 0.12. You go back there, you notice that we divide both sides by 84,000.021. And hence, we get 0.4762. When you have it like this, you can introduce natural log, meaning that this is now going to be the power. So you have something like this. You have E raised to power, the same number there, 0.4762 being equal to V2 over 0.12. V2 over 0.12. So like that, you can even now cross multiply, taking us to this. So that's how come you have that one there now. This is from your expression when you're dealing with indices and logarithms, how they relate, interpreting from one form to the other. So then our V2 is 0.1932. Our V2 is 0.1932. Heat transferred for each of the processes. For isothermal, we already told we're given 40 kilojoules. Adiabatic, you don't transfer any heat. The other isothermal, we told the efficiency is 50%. So what is 50% of 40? 50%, we just say heat rejected over heat received, and there our efficiency is 0.5, meaning you end up with 20 kilojoules. But remember, we're saying this is heat rejected. This heat is being rejected. So hence, it's negative 20. The last one, which is the adiabatic compression. In any adiabatics, the heat transfer is 0. So these are the heat energies in kilojoules that have been transferred for each of the 4 processes. Let's go to the last question. So here we've been given a steam engine, a bore 375 millimeters, stroke 500 millimeters, diameter 50 millimeters. Then we need to calculate the, let's check. Excuse me. So trial was conducted, and this is what was recorded. Just a minute. Cover end on the indicator diagram, area 2640 millimeter square, crank end 2